Hello everyone. So this is our fifth lecture in our complex lecture series topic. So the topic is the digital to analog converters. So if we talk about digital to analog converters, so that means we are provided with a digital signal. That means the information is in binary format 1 0, and we are trying to convert that information into a continuous domain signal. Maybe we can say the most familiar system in which the values are represented in continuous form is the decimal one. So that means anything which is converting the binary format type into digital format type, so it can be termed as a digital to analog converter. So this thing we had covered in our very first unit, that how we can convert a digital signal or a binary signal into a decimal signal. So this was the, if you are able to remember, that if you are provided with a number, let's say if you are provided with a binary number B2, B1, B0, how this is going to be converted into decimal one is simply multiplying B0 with 2 raised to power 0, multiplying B1 with 2 raised to power 1 and B2 with 2 raised to power 2. So this is how we had converted a binary number into a decimal number. So this is a generalized expression written for converting a n-bit binary number, n-bit starting from 0th bit and till n-1. So a total of n bits are there in the binary number, and we have to convert that binary number into digital, into analog. Analog means continuous domain signal. So this we can see that B0, here nothing is mentioned, so we can treat it as 2 raised to power 0. Here B1 into 2 raised to power 1, B2 2 raised to power 2. Similarly, Bn-2 into 2 raised to power n-2, Bn-1 into 2 raised to power n-1. And this k is the proportionality factor. Ideally, this k should be equal to 1, so that there is 1-on-1 mapping. That means there is no difference between the analog and digital value in terms of their magnitude. Okay, so if that k is equal to 1, then that digital value will be and its analog value are 1-on-1. They are not scaled. That means if I am applying 101 on the digital scale, then I will be getting 5, because 101 is equivalent to 5 in the decimal scale or in the continuous scale, analog scale. Okay, and for this to happen, for 101 to get 5, this k should be equal to 1, else this k can be a scaled factor as well. That means this k can have any magnitude depending on the external components which we will be using when we will be preparing the circuit for a D to A converter. Okay, so this is the basic logic how we are going to convert, that we are provided with some binary values 0 0 0 0 0 1 and moving till 1 0 1 1, that means 11. So this in amplitude output signal, if k is equal to 1, then this is equal to 0, this is equal to, for this particular point this should be equal to 1, for this particular point this analog value should be equal to 2, for this should be equal to 3, 4, similarly for this it must be equal to 9, and last one 11. Okay, so this is how we will be feeding some binary information or digital information, and that digital information will be converted into analog information or a continuous domain information, or in simple terms we are saying that we are converting a binary information into decimal information. That binary to decimal is equivalent to digital to analog in our case. Okay, so that means we will be providing some binary information to digital to analog converter, and we will be getting some continuous domain signal. Okay, this is just a example that if you feed this, you will be getting some continuous domain signal, and it is not the exact case that if you feed this to DAC you will get this. So this is not the case, but this is just a general block level representation, that how a discrete signal or a digital signal is being fed to DAC and a continuous signal is being obtained at the output of the DAC. So there are generally two methods, binary weighted resistor method and R2R ladder method, and in both the methods we are using switches, resistors, op amps. Okay, so these are the three things which we are going to use while preparing the circuit for our D2A converters, whether we are preparing binary weighted resistor or we are preparing R2R ladder structure. Okay, so this is the circuit for weighted resistor digital to analog converter. Why it is called weighted resistor? Because it is called weighted resistor because in this you can check that these resistance values, it is R, or R we can say 2 raised to power 0 R, because it is equivalent to R. Then 2 R can be referred as 2 raised to power 1 R. Similarly 4 R is equivalent to 2 raised to power 2 R, and this one 2 raised to power n minus 1 R. That means for n bit I am going till 2 raised to power n minus 1. So we can check that all resistances are of different values. All resistors are of different value, and that different value is in scale of 2 raised to power 0, 2 raised to power 1, 2 raised to power 2 and so on. Okay, so weighted resistors are used to distinguish each bit. So that is very much clear to me that if I am marking my bit as MSB, most significant bit, that means the resistance of that most significant bit should be minimum. Only then it can have maximum value. And similarly in case of LSB, least significant bit, that means minimum significance should be appearing from that branch. So in that case resistance should be maximum. So out of this we can see that this 2 raised to power 0 R is the minimum resistance. Okay, and this 2 raised to power n minus 1 R, this is the maximum resistance. Okay, so for this minimum resistance I am labeling this terminal as my most significant bit, and for this maximum resistance I am labeling my input terminal as least significant bit. Okay, so this is the general pattern, MSB to LSB, and there is an op amp structure. So to use this structure, to derive expression for this structure, we should be first aware of the connection pattern, or we can say that how this op amp is going to function. So for that thing we should be aware that if that op amp is going to be used in inverting configuration, there are two configurations with op amps. If you are using this as in this format, okay, this is my input resistance R1 and this is the feedback resistance RF, okay, and this is my output V0. So in that case output V0 is equal to V in into minus RF upon R1. Why minus sign is there? Because we are applying the input on the inverting terminal and the positive terminal is grounded. Similarly, if I am opting for this configuration, okay, there is a resistance here. In that case, this V0 will be equal to 1 plus RF upon R1 into V in. Okay, so I am going to use this configuration, this expression. So we should be very much aware that output of op amp in this scenario in inverting configuration is equal to input into the ratio of the resistances, feedback resistance and input resistance. R1 is the input resistance. So we can see that in this scenario, this op amp this terminal is the aggregate of multiple input terminals. Okay, that means voltage will be reaching this terminal from multiple inputs, and the aggregate will be considered as the input to the op amp. So we can see that in all these cases input resistances are different. So which we have mentioned here as R1. So this is not R1, this is not a static resistance R1 in all the cases. This R1 is changing its value as R, 2R, 4R, 8R, 16R and so on. Okay, and from these we can see that these terminals are getting connected either to 1 or 0. Okay, this 0, for 0 we can see that this thing is connected to V0, that means voltage corresponding to binary 0, and this thing is connected to V1, that means voltage corresponding to binary 1. Okay, so this is the structure of weighted resistor R2R network, weighted resistor D2A converter. So again, a freshly drawn circuit, it is the same circuit which was designed in the previous slide. So again, this is the MSB corresponding to the minimum resistance, LSB corresponding to the maximum resistance. There are different currents from different branches, and all those branches are aggregated to produce a sum current which will be translating into a voltage signal, because eventually we are going to use op amp in voltage mode. Some voltage will be available here at this terminal corresponding to this current I, and the overall resistance, this overall resistance depending on, and these resistance, which of the resistance will be participating will be depending on the binary information which we will be applying here. So if we are, let's suppose we are applying 1 0 1 1, let's suppose, that means this corresponding to this 0, this resistance is not going to participate in this circuit, because that switch is getting connected to this 0 position. So that means the presence of this resistance, this resistor, is nullified. Okay, and rest of the resistance will be utilized for calculation of the actual voltage, because the binary information at these three terminals is equivalent to 1. That means for these three cases this V1 is going to be effective. Okay, and this is the sum current of multiple branches which will be reaching here. So if we are going to write an expression for this, so let's write an expression for this now. This V0, output V0 will be equal to, okay, will be equal to V in, and if I am labeling them, let's say for the first branch, let's say for this branch, and this, let's suppose it is Vn minus, for this In minus 1, I am utilizing this as voltage Vn minus 1, because this is MSB and this is LSB. So this must be equivalent to, if voltage is appearing from here, it will be equivalent to V0. Okay, so V0 will be equal to Vn minus 1. This is the input voltage for this branch, first branch, this branch only, and the resistance ratio Rf minus Rf upon R. But the thing is, this will be only effective if this bit position B n minus 1 is there. That means if this Bn minus 1 is equal to 1, only then this branch will be producing some legit output which will be reaching this op amp's terminal. Otherwise, the overall effect of this branch will be 0 if this Bn minus 1 is equal to 0. Similarly, if you proceed further for the second branch, for this branch, this will be having voltage Vn minus 2 into minus Rf upon R1 minus Rf upon 2R. Okay, minus, because this, the resistance in this second branch is 2R, into Bn minus 2. Similarly, proceeding further, Vn minus 3 into minus RF upon 4R into Bn minus 3. Okay, and similarly the last few branches will be, this will be the last one, need not to say, B naught into minus RF upon 2 raised to power n minus 1 R, this thing into V naught. Okay, so this will be the last one. And if we are going to write the middle one more step from the LSB side, it will be V1 into minus RF upon 2 raised to power n minus 2 R into B1. Okay, so this is the overall expression of this voltage at this final output. But one thing has to be very much clear, that all these Vn minus 1, Vn minus 2, Vn minus 3, all these different voltages, these things cannot have multiple values, because for this V naught will always be, we will be treating this V naught voltage corresponding to 0, binary 0 is equal to 0 volt, and voltage corresponding to V1 I am treating it as minus VR. Okay, minus VR, reference voltage for binary 1. That means if in case any branch is activated, voltage in any of these branch, this Vn minus 1, Vn minus 2, Vn minus 2, Vn minus 3, V naught, V1, the maximum voltage or minimum voltage, minimum it can be 0 and maximum it can be minus VR. And we have already multiplied it with their binary bits. That means if these binary bits are 1, then at all these places, Vn minus 1, Vn minus 2, all these voltages will be equivalent to VR, because they are corresponding to 1, V1 corresponding to VR. Okay, so if you write the expression, modified expression for this one, we can simply write it as minus VR into minus RF upon R, okay, into Bn minus 1. Then next one again minus VR minus RF upon 2R into Bn minus 2. Similarly, if we reach the second last stage, this one, we will be writing it as VR, again minus VR, and it will be minus RF upon 2 raised to power n minus 2 R into B1, and last one minus VR minus RF upon 2 raised to power n minus 1 R into B naught. Okay, so if we take common, so we can see that VR is common, RF upon R is also common, and let's suppose I am taking this 2 raised to power n minus 1 R outside the bracket. So what will be inside? Okay, so this is taken out, this is taken out, and instead of taking R out, I am taking 2 raised to power n minus 1 R out. So this Bn minus 1 will be multiplied with 2 raised to power n minus 1. Okay. Similarly, this Bn minus 2 will be multiplied by, this thing is Bn minus 1 into 2 raised to power n minus Bn minus 2 into 2 raised to power n minus 2, and similarly proceeding here, it will be B1 into 2 raised to power 1 B0 into 2 raised to power 0. So this will be the overall expression. Now we can see that the thing inside the bracket, this the common term, this can be referred as the proportionality factor K, which we had stated in the very first slide, this thing K. Okay, so this is the value of the proportionality factor K, and rest of the things are simplified in simplified terms. B0 into 2 raised to power 0, B1 into 2 raised to power 1, B2 into 2 raised to power 2. Similarly, proceeding further, B n minus 1 into 2 raised to power n minus 1. So this thing we are getting, and this K, for this K equal to 1, if I want that K should be equal to 1, then I should be very much clear that this VR should be equal to 2 raised to power n minus 1 and RF should be equal to R. So if I am able to ensure these two things, then this complete thing can be considered as 1, because everything will cancel out each other in the division part. Okay, so in this way we can see that I am able to generate this expression which is exactly equivalent to this binary to decimal conversion expression. Okay, so in this way we can say that we have successfully converted a digital signal into an analog signal. So now some advantages and disadvantages. So this weighted resistor DAC is having simple construction, fast conversion, and some disadvantages: it requires large range of resistances. That means for n bit conversion I require n distinct valued resistances. That means if I am going to design 12-bit DAC, then 2 raised to power 1, 2 raised to power 2, 2 raised to power 3 up to 2 raised to power 20. That means that many different resistance values are required, and these need to be highly precised. These need to be highly precise for accurate D to A conversion, which is a tough task to achieve. And the next one requires low switching resistance in the transistors. Actually, these resistances, if we are going to implement in this IC form, then these resistances are going to be replaced by actually transistors, and those resistances are low. Those low resistance are quite difficult to incorporate in form of transistors due to different values of resistance, and depending on their precise values, this arrangement can be quite expensive. Therefore, usually limited to 8-bit resolution. That means if we are interested in preparing 1-bit, 2-bit, 3-bit up to 8-bit D to A converters, we can opt for this method, because for that 2 raised to power 8 or n minus 1, if we say 2 raised to power n minus 1, that means 2 raised to power 7. 2 raised to power 7 is 128 kilo ohm. Okay, 128 kilo ohm. That means that we will be reaching up to 120. If 1 kilo ohm is the minimum resistance, then the maximum resistance will be 128 kilo ohm. So that much wide range of resistances will be required to prepare weighted resistor D to A converter. Okay, so with this, the upsides and downsides of this weighted resistor DAC. Now we will proceed to the second D to A converter, which is R to R ladder DAC. Why we are going to use ladder? We are saying because the vertical branches are of 2R values and these horizontal resistances are of value R. So that's why one of them is R, then 2R, R to R. So this prepares the R to R ladder structure. So that means the best part of this is we are not going to use wide range of resistor values. We are going to use only 2 values of resistances. That means we can design this R to R converter using any 2 resistances which are in which the values are, one of them is R and second one is R. That means I can design this complete structure using 1 kilo ohm and 2 kilo ohm resistance, which is a quite easy task to fabricate. Okay. So the inputs to the resistor network are applied through the digitally controlled switches. So these digitally controlled switches from these 2R vertical branches from all these vertical branches, we can see that there is a switch. Using that switch, either 0 can be connected or 1 can be connected. You can see that for 0 it is connected to ground, and for this 1 it is connected to reference voltage VR, which was the exactly similar case in case of weighted resistor as well, in which we had used 0 volt for binary 0 and VR for binary 1. So these are the multiple branches. So this can have, there can be n number of bits. This dotted section is represented that there can be n number of R2R branches to prepare n bit R2R ladder DAC. But if we are interested in preparing 3 bit, because we for us to realize the expression for this R2R structure, we cannot go for n bits. We are taking example, let's suppose n is equal to 3. That means we are going to prepare 3 bit R2R ladder type DAC. That means this could be the structure, this could be the, this is my MSB, this is my MSB B2, this is my LS, this is the middle one B1, and this is my LSB B0, B2, B1, B0. That means 3 branches are there, okay, and this last one is the grounded branch. So to realize this, I am taking different scenarios. That let's suppose the voltage is appearing only at the LSB side. So if voltage is only appearing, that means I am going to take 3 cases. 0, 0, 1, that means high voltage at LSB only. Then I will take the second case 0, 1, 0, then third case 1, 0, 0. So for the time being, I am taking the case 0, 0, 1. That means here B1 is equal to 0, B2 is equal to 0. So in that case, this complete structure, if I am going to calculate what is the voltage here and what is the effective resistance of this network, what is voltage here and what is resistance here. So I am going to calculate that. So this can be calculated with the help of Thevenin's theorem. So I am considering at this interface, let's suppose at this interface I am going to calculate the effective voltage and effective resistance. Then I can see that this R2R are in parallel. So at this XX interface, the parallel combination of R2R, 2R and 2R will be equivalent to R only. That means at this XX interface, the resistance is R only, and this VR is divided among these 2 resistances. If I connect these 2 branches together and apply Thevenin's theorem on this XX interface, then I can see that this voltage will be divided as per the voltage divider rule. If this is the voltage which is going to be divided amongst these 2 resistances, which are of values 2R and 2R. So how it is going to happen? VR across this XX interface, because this XX interface is having this 2R resistance. So voltage across this 2R resistance is equal to VR into 2R upon total resistance 2R plus 2R. That means it is equivalent to VR into 2R upon 4R. That means equivalent to VR by 2. So you can see here that the effective voltage at this X port is VR by 2. Similarly, now again applying Thevenin theorem at the Y interface, again this R plus R becomes 2R, and this 2R and this 2R are again in parallel. So at this YY interface, effective resistance is R, that means 2R again. So at YY interface, the resistance is R, and again this voltage, now this VR by 2 will be divided amongst these 2R and 2R. So it will become VR by 2 square. And similarly, if we proceed further, that there is R and R, these 2 becomes 2R, and at this ZZ interface, again applying third time Thevenin's theorem. So for this 2R, you can see that this 2R and this 2R are again in parallel. So effectively at ZZ interface, again the resistance becomes R, and the voltage is going to be divided one more time. That means it will become VR by 2 cube. And this R and this 2R, because only this 2R is left beyond this ZZ interface. So this R to R becomes 3R. Okay. So effectively we reach this circuit, VR by 2 cube. So this is 3R and this is my voltage VR by 2 cube if I consider the case 001. Similarly, if I take the case for 001, I found that the resistance voltage is VR by 2 cube and the effective resistance is 3R. Similarly, for this, if this would have been 010, then I can see that this division would have not happened on this XX interface. If those values would have been 010, if it would have been 010, then there would have been no division here because there is no voltage here. The voltage would have been first appearing for the first time on this middle one, B1 bit. That means it would have divided first time here and second time here. That means VR would have been divided only 2 times. That means the voltage in this case would have been VR by 2 square, and resistance is not going to change in any of the cases because the values of resistance in whether I apply 010, 101, 110, any cases, the resistance network is identical for all the cases. So this resistance is going to remain the same. Similarly, for the third case, if I consider this as 100, for 100, that means 1 is 0, 1 is here, 0 is there, 0 is there. That means first time voltage will be appearing here only. That means it will be divided at the ZZ interface for the first time. That means it can only be divided once by 2. That means for the third case, my voltage will be VR by 2 raised to power 1 and resistance will be 3R. Okay, so these are the 3 cases which we have derived from the R to R structure. That means if LSB is considered, LSB means B0 is, if B0 is equal to 1, then voltage is VR by 2 cube, resistance is 3R. Similarly, if MSB is 1, that means B2 is equal to 1, then voltage is VR by 2, resistance is 3R. And if B1 is equal to 1, then voltage is VR by 2 square and resistance is 3R. So we have considered all 3 cases one by one, and if more than one bit is simultaneously high, then more than one branches, that means both either 1 or 2 or 3 or any combination of these voltages may be appearing at this terminal. Okay. Now again applying the rule for the gain of the inverting op-amp configuration, again we can see that now for all these cases, as in we have seen that in case of weighted resistor, the resistance of all branches were different, but here in this case we can see that the resistance of all the branches are identical and equivalent to 3R. So I can write the expression as RF upon 3R for all the cases, RF upon 3R, VR by 2 cube because this is the input voltage, into B0. Why B0? This LSB corresponds to B0. So this is the first part of the expression. For this second part, VR by 2 square, RF upon 3R, this is identical for all the branches, into B1, this bit position. And this last branch, voltage is VR by 2, that means VR by 2 raised to power 1, and resistance RF upon 3R, and this is my MSB B2, so that's why B2. So this is a overall expression, and if I take RF upon 3R common and VR upon 2 cube common from this expression, I can see that inside the bracket I am left with this expression that can be treated as 2 raised to power 2 into B2, 2 raised to power 1 into B1, and 2 raised to power 0 into B0. Okay. And this complete thing can be considered as the proportionality factor K, that should be ideally equivalent to 1. So for K is equal to 1, my RF should be equal to 3R and my VR should be equal to minus 2 raised to power 3. Okay. so that this minus gets cancelled out. So if I am going to use these values, then this k will be equivalent to 1. Okay. So this is how we have derived the expression for R2R ladder type DAC. Now coming to the advantages of R2R. The best part is only two resistance values are used, R and 2R, and it does not require high precision resistances because we are not interested in vast range of resistances as we had used in case of weighted resistor, where we had used R, 2R, 4R, 8R, 16R. But in this case, we are not going to use multiple values. We are only interested in R and 2R. So it is very much convenient for me to implement. And the disadvantage is lower conversion speed than binary weighted type DAC because it is slightly complex network. So conversion speed is slightly on the lower side. So with this, we come to the end of this lecture. Thank you. So with this, we also come to the end of the complex lecture series for this subject.